Yeah, thanks a lot. Thanks a lot for the invitation. It's an honor to speak here. And it's really nice to be back. I was a member to 2014 to 2015. So it's really nice to come back. It's wonderful. Okay, so my field of interest is in differential geometry, in particular conformal geometry geometric analysis. So today I'm going to report to you some Yamabi flow results that I recently did with Gilles, Carron, and Chen. Okay. All right, so let's first start with what is the Yamabi problem. And this is the problem in differential geometry about finding a constant scalar curvature metric within the same conformal class. So given a Riemannian manifold compact, dimension bigger or equal than 3, and people ask whether there exists a constant scalar curvature metric in the same conformal. You have some arbitrary shape to start with, and you want to find some uniform metric or some kind of canonical metric in the same conformal class. All right, so the problem is equivalent to the following PDE problem. So if you write everything in terms of the conformal factor, so G and G naught are conformal change to each other, so they're only up to a conformal factor, and then you write down the equation for the scalar curvature of the new metric, and you want it to be a constant scalar metric, a constant scalar curvature metric. So you just want to solve this equation 1 for the right-hand side, this factor to be constant C. So this problem was first, well, actually asked by Yamabi, and he solved it, and it turns out that it's only, well, partially solved. And then there are people trying to make the argument work. So this is a combination of work of Yamabi, Schrödinger, Obang, and finally completely solved by Chen.
So an is some function depending upon n, it's a constant, an.
An is a dimensional constant. Yes. All right, so in the 80s, Hamilton proposed to consider the problem, but using a heat flow method. So he wants to say whether there would be an evolution equation that could start from this initial metric G naught and then evolve with certain rule, and then finally converge to some metric, and that metric is the constant scalar curvature metric. Okay, so in the the flow he considered was this Yamabi flow, in which the evolution was given by minus scalar curvature times G. So partial TG equals minus scalar curvature times G. Well, if it is in the compact case, then we really want scalar curvature tends to the constant, and that's what we call the normalized Yamabi flow. In other words, instead of looking at the right-hand side here, one looks at the constant C minus R, parentheses times G. In other words, in the steady case, so the flow will tend to the case where the right-hand side tends to 0, so that the scalar curvature tends to that constant C. So so as before, the evolution equation could be written in terms of the conformal factors evolution equation. So you can write down the equation for this metric. Metric is a n by n matrix, and using the local coordinates. But you can write it down in terms of the conformal factor, and it becomes an evolution equation of the function u. And this equation is just given by number 3. As you can see that the right-hand side is basically just some Laplace Laplace operator acting on U, well, you add some curvature terms, and the left-hand side is not partial TU, it's partial TU to this nonlinear power. But roughly speaking, it's some heat flow type, and people tries to use the heat equation type of analysis to understand it. All right, so there are many results in the Yamabe flow, and for compact manifolds, as I mentioned earlier, that was the initial motivation. So people tries to use it to study the Yamabe problem. So in dimension 2, this actually gives another proof of the uniformization theorem in dimension 2. It was a work by Hamilton and as well as Chow. And in dimension higher or equal than 3, this is the real Yamabe problem that we were talking about. And Hamilton first proved that the Yamabe flow always has long time existence. So this is different from other type of geometric flows like the Ricci flow. Ricci flow doesn't necessarily have long time existence, but for Yamabe flow, Hamilton proved that. And then under some positive Ricci curvature condition, Chow proved the first convergence result in 92. Afterwards, Rugang Ye gave a proof in 94 on locally conformally flat manifolds. And this one was actually crucial because at that time, the Obang has already proved the Yamabe problem for all higher dimensions or non-locally conformally flat manifolds. So the only non-trivial cases left for the Yamabe problem back then was the case for the locally conformally flat manifolds as well as lower dimension from 3 to 5. So that was a really nice result. Okay, so after that, the Schwartlich and Struve in 2003, they proved the convergence of Yamabe flow between dimension 3 and 5, and under this condition that the initial energy is small. And Brendel in 2005, so he removed this small initial energy condition. So the flow always converges for lower dimensions.
So what is the energy? Gradient of Ricci curve shows.
This energy is yes similar to that, but it's actually
Yamabe's. It's the Yamabe
energy, yeah. So Yamabe.
one that he.
Right. So it contains this gradient U L2 as well as some scalar curvature weighted L2. But it kind of gives intuitively it's some that we want to know.
I mean, it's very closely related to the variational method. I mean, in the variational, in Chen's proof, you just directly attack. So I show there's a minimizer.
Right. Yes.
Here you don't. It's the gradient of the same.
It's a gradient. Yes. Yeah. I should have mentioned that. So the Yamabe problem is actually a variational problem. So maybe let me come back to that a little bit to repeat what Peter has pointed out. So this problem, even though it looks like you're solving an equation, but actually this equation is a critical point of some functional. So in other words, when you're trying to find the critical point, you are looking for, you can do it by finding the minimizer. Right? So if you could find the minimizer of this functional, then you find a critical point of this equation. And finding minimizer, the most intuitive way is to run a flow and or gradient flow along certain directions so that it decreases most efficiently. And this gradient flow is actually given by the Yamabe flow. So Yamabe flow is the gradient flow of this variation structure. All right, so Okay, let me come back to here a little. So the Brendel in 2007, he also proved for higher dimensions. So this is dimension bigger or equal than 3. Bigger or equal than 6. So he proved the convergence of the Yamabi flow, but under some very mild curvature, wire curvature vanishing conditions. So still needs a little bit condition, but it's pretty good result.
Is that the last divide tensor condition, is that automatically true in low dimensions?
It could only be seen, I think it could, but the method seems to be different. The method seems to, this wire tensor condition is something like, so using this wire tensor condition, the strategy is very similar to Aubin's 76 proof. So basically they are trying to construct some test function to prove that this, in Aubin's work, it tries to prove the Yamabi constant is strictly less than the Yamabi constant of the center sphere. And somehow in the flow method, you can see the parallel picture. The method in lower dimension does not work in higher dimensions, and he needs this extra condition to construct special test function there. Okay. So our goal is to study the Yamabi flow on non-compact manifolds, so non-compact complete manifolds. We're trying to, well, this problem is too wide and it's very hard to control what's the behavior near infinity. That's the main difficulty. And usually in the heat type equation, you need to give certain prescription as a boundary condition to control the behavior of the flow. So the most one natural family of manifolds that we consider is the asymptotically flat manifolds. So the definition is very easy, and it's just that you have a Riemannian manifold, and at infinity, it's diffeomorphic to the Euclidean space outside of a big ball. And the metric of this manifold near the end, so we call this the end of this manifold M. The metric of that is similar to the metric of the Euclidean metric with certain weight. And if tau is bigger, tau is positive. If tau is bigger, it means it decays faster. And correspondingly, the derivative decays in a corresponding derivative order.
You're going to put a condition on how big tau must be?
Yeah, that's a very good question. So in order to define the ADM mass that I'm going to talk later, that one needs to give a certain range of tau so that the ADM mass is well defined.
And do you need this for all alpha or just some range of alpha?
Yeah, that's a very good question. So people usually consider about, for example, curvature. So they usually put tau alpha bigger or equal than 2, and sometimes they need to take derivative of curvature. So it depends on the context. But usually there is some like alpha bigger or equal than 2 or bigger or equal than 3. Things like that. But you can certainly
all alpha that you would need it.
Depends on the problem that you want to.
But for example, in your work here.
Yeah. So in my work, we assume alpha bigger or equal than 3, and then we can prove all the do all the analysis that is needed. Right. But the metric is smooth. So the metric is smooth. It's just the decay rate, whether you need that much of decay in.
But variationally, I assume Chen and others have studied this non-compact case too, asymptotically flat.
Yeah.
You're recovering what they have?
That's a very good point. So Rick Chen, in his proof of his 84 paper of proving the Yamabi problem for the compact manifold, he actually needs to use the positive mass theorem for the non-compact manifold. And but the positive mass theorem, I think, is so our problem doesn't give a proof of that. Our problem proves that gives another proof that the mass is minimized by this scalar flat metric in the same conformal class. I'm going to point out.
Okay. I'm just comparing flow methods with variational methods.
Yes.
I want to calibrate that. Yeah.
Yes. Yes, they're highly related. And there are always the parallel pictures there. Okay. So this is the thing that I'm going to remark. So first of all, in general, one can deal with asymptotic flat manifolds with multiple ends. So it doesn't necessarily need to be just one end. And in my previous definition, it only has one end because I use Rn, subtract the compact 4. So I assume the one end, but all the techniques, at least in my paper, apply to finite many ends as well. So it's just for simplicity that we assume there's only one end. Okay, the second thing is something related to the ADM mass that Peter mentioned earlier. So ADM mass is it's something coming from math physics. So it talks about the behavior of the metric at infinity, and it's an invariant that measures the global geometry of this metric for asymptotic flat manifolds. So mathematically, one gives the definition as the following. So it's the limit and of this integrals, but this integral depends on the choice of coordinate at infinity. So if you just read it virtually, but it turns out that this is I think this is the work of Bartnik that says that it only depends on the metric itself. It's independent of the choice of coordinates. No matter how you make your clever choice, take the integration and take the limit, it finally gives you the same limit number. So it's something intrinsic in the geometry, and later on, people will find out that it's very much, in general, it's very much related to the global behavior of the scalar curvature. But that's just a very hand-waving idea.
So what's the intuition behind this expression? Why do we think of this as a mass? Of this limit of this?
Yeah, that's a very good point. I think there is a very special case that I like very much that says that this M of G. So if the manifold is actually a graph, assume in addition that is a graph given by some f from, let's say, Rn to R, right? And you embed this, you have this manifold, but in general, it's not necessarily a graph. But assume that it's a graph. This M of G defined this way actually can be written as the integration of the scalar curvature over certain, I forgot the power here, but it can be written this way. So it's some integration by parts formula when it's a graph, it could be proved that it's the integration inside of all the scalar curvature, but with certain weight given by this graph's volume area form. But in general, if it's not a graph, there's not such a beautiful global quantity, and I really think it's a very magic thing that people realize this is something variant and
even in dimension 2, it's a very subtle invariant in conformal mappings. It's related to normalization of a conformal.
So for the Euclidean space, this mass is 0.
sorry, say that again.
The Euclidean mass is 0, right?
Yeah, for the Euclidean matrix, yeah, this mass is 0.
So what is new here?
Yeah, so the ADF for the ADM mass, the most famous and important result is that there is a positive mass theorem. It says that if you have a metric that is, so if you have a asymptotic flat metric on which this masses were defined, and if you have the scalar curvature non-negative, and scalar curvature is in L1, so L1 integrable, then this ADM mass must have been non-negative. And also it is equal to 0 if and only if the metric is a Euclidean. Right. So it gives the converse statement of what you just mentioned.
So what is the physically realistic value of tau?
Realistic value of tau.
Yeah, if I had some masses, but what would it actually do? Be n-2 or?
Right, that's a very good point. So, so here, one needs to have tau big enough in order to define this. Otherwise, it's not integrable. But on the other hand, tau needs to be strictly less than n-2. Yes, n-2, because if tau is too big, one can actually show that this one vanishes, is identically equal to 0. So in other words, if you have too much decay at infinity, and those derivatives are pushed too low, and when you take the integration, it vanishes. So the
That's not going to hurt you for your theorem. That's not going to hurt you in terms of your theorem, is it? The bigger tau, the better.
In my theorem, it doesn't. But,
Right. But in terms of their physical interpretation.
The physical interpretation of ADMS means a reasonable range, and this range is from n-2/2 to n-2. Yes. Okay, so before giving the theorem, let me just introduce two notions, and we're going to use that in our statement. So this is just the weighted Sobolev space and Holder space. So it looks complicated formula, but let me just say they are weighted LP space and WKP space, the Sobolev space, just by adding the suitable power of R at infinity, so that the function is in LP, and in the meanwhile, the function behaves roughly like R to the beta power at infinity. And here beta is a real number, so it allows to be growing as well as decaying. At this moment, it's not necessarily to be a positive number. Okay, so similarly, Bartnik also defines the Holder space, the CK alpha. So first you define the C alpha and CK, and finally you put them together to get CK alpha. So this is just the usual Holder space, but together with this weight constraint at infinity. Okay, so let me say what we want to study, the questions that we want to study. So for the Ricci flow, there are studies about Ricci flow on asymptotically flat manifolds. Of course, Perelman's work is about Ricci flow on compact manifolds, and later on, people have studied about Ricci flow on non-compact manifolds, and in particular, asymptotic flat manifolds is one special class of interest. So, what was known before for Ricci flow is listed here. First of all, you have short time existence. So you started with a metric. So asymptotic flat roughly looks like this. So at infinity, it's roughly like Rn, but inside it might have topology or something else. This is the asymptotic flat manifold to start with, MG0. And the Ricci flow tells us that you run the flow, and as t positive, your flow will become a different place, maybe like this. But it preserves. So first of all, it has short time existence, and also it preserves to be asymptotic flat. So it won't happen that suddenly it drops the asymptotic flat structure. It becomes something like this, or going to infinity. It won't happen. Okay, and what about the mass? It's really interesting to see that from pure computation, one can know that the ADM mass is actually preserved under the flow in a lot of cases, depending on the dimension and depending on the tau, the range of tau. But in a lot of cases, it's just invariant. And then people wonder what happens. Because we have this positive mass theorem in our mind, so we start from an arbitrary shaped manifold, we run the flow, the mass stays the same. However, if the flow finally converges to something canonical, maybe the Euclidean metric, flat metric, maybe some other canonical metric, that might have a certain rigidity that gives the ADM mass is equal to a certain number. Then what happens is that what's the procedure of this? The mass stays the same, and suddenly it may have a jump, may have a gap. So all of this is just a rough description, but that really depends on what happens in long time, whether the flow exists and converges in long time as time goes to infinity. Okay, so for the Ricci,
I'm confused. I thought you said that Hamilton already proved that the Yamabi case has long time existed.
that's for compact manifolds. That's for compact manifolds. Yeah. Here we are talking about asymptotic flat.
Because of course Ricci has singularities on the compact too.
Yeah, right.
It's very different.
Right. So the long time existence is that for the Ricci flow, people know that there's no long time existence because it may develop singularity in finite time. And for example, in dimension 3, you could.
Yeah. So this is all just about the ends.
So it's all just about ends, right? So this is the work of a recent work of Gilles, and he proved that if the Ricci flow has long time existence, suppose it has long time existence, then it actually converges. So it won't happen that you have some wild behavior at time infinity. So in other words, the blow up for singularity would not happen at infinity. You have certain control as long as it has long time existence. And Lee used this to give another proof of the positive mass theorem in dimension 3. Why? Because as long as you have this result, so suppose you have long time existence, then it implies convergence. But what happens is that for a general initial metric, you might develop singularity. So in dimension 3, Perelman's result says that you can play this, perform the surgery, and there are only finite many surgeries if the surgery area is not too big. And you can control that size and make finite many surgery. And after finite many surgery, after the last one, it has long time existence. And by this result, it tells that that would give the long time convergence. So you basically have the whole piece of information that this manifold topological type and all that, and you can show the ADM mass is always preserved under this one, and it's finally converged to something, and you know that is the Euclidean metric, the limiting case after the surgery, and you're able to give a positive mass theorem, another proof in 3 dimensions. Unfortunately, it cannot give the positive mass theorems for all higher dimensions, which I think is still an open problem.
Next question. Yes, but what happens, for example, if I take a plane and glue in a handle so that the curvature is always negative, so Richie should enhance it, but it stays there. So what happens then?
So when you have a you mean Ricci flow? So
Yeah.
then you would have singularity. You would have like handle type singularity, but then they can show there are only finite many singularities. And for example, you after you remove a handle, it will be in a certain shape, and eventually it will go to the Euclidean space. And the good thing is that when you remove this handle, when you do this surgery, the mass is in a good direction. So they basically, I think that part technically is not very difficult in the sense that this integral is at infinity. So as long as you control this weight good enough, it won't affect this limit of this integral over a very big sphere. So that's why the mass is not influenced under the surgery. Okay, so let's come back to here. What happens for the Yamabe problem that we are interested in? Well, we know there is a short time existence as well as the preservance of asymptotic flatness and AEMS. This is by work of Chen and Gilles, and I think it's 2015. And we are wondering whether there is long time existence. We're wondering what happens to the convergence of this flow. Okay, so let me just list the results here. So this is the work of with Eric Chen. So we proved that first of all, there is long time existence for this Yamabe flow without any curvature condition. So we need to assume. So here I should point it out. For simplicity, I didn't wrote k should be bigger or equal to 3, and this tau is strictly positive. That was our.
So you're proving the analog of Hamilton.
Right. This part is the analog of Hamilton, the asymptotic fact case. Okay, so in the Ricci flow case, we knew that it may not. So in the previous slides, as I mentioned, there's no. In general, there's no long time existence. However, there are some cases, for example, if you impose Ricci curvature is non-negative, you have some results in that which says it still has long time existence, but it requires some curvature condition. In general, it must develop singularity. Okay.
But you got no, remind me what AF is?
Oh, that's asymptotic fact.
So it's general.
Yes, yes,
Completely general.
it's very general, right? Yeah.
So it opens the door to prove Shane's theorem for the flow, if you can control the convergence.
We can. Well, the problem is that this one converges to scalar flat metric. It may not converge to the Euclidean metric in that positive method. Yeah. Okay, so the second part is about the convergence, as I mentioned earlier. So after we know the long time existence doesn't require any assumptions, we want to see whether the convergence doesn't require anything. But it turns out that it requires certain thing, but it's pretty neat requirement so that we only need the Yamabi constant is positive. So under the condition that the Yamabi constant is positive, there exists a limiting metric G infinity, and this convergence is in a global weighted sense. So CK plus alpha minus tau prime. And here, I should say that this tau prime is strictly less than the minimum between tau and n minus 2. So in some sense, the n minus 2 comes into play a role here, and it's good that it's in the same range as the masses were defined. Okay, So G infinity is the limit metric, and G infinity actually one can show that it is a scalar flat matrix. In other words, scalar curvature of G infinity vanishes. But it's not necessarily the Euclidean metric, because it's just one equation on this conformal factor, and there are many functions that satisfy this. Depending on the initial conformal class that you started with. If you started with the Euclidean matrix conformal class, it will eventually go to the Euclidean metric as the only one. But otherwise, it would not necessarily go to the Euclidean metric. Okay, so what is this Yamabe constant that I imposed as a condition? So the Yamabe constant is defined in the following way in this non-compact setting. So a lot of people are very familiar with Yamabe constant in the compact setting, but here is the non-compact manifold, and we need to define it with a little bit subtle choice of the function. So U is a compact supported smooth function, and U is not U is not zero, because U is going to be the conformal factor. And you take this quotient. This is the same as the expression of the Yamabe constant. So you would in general have Y bigger than zero, Y equals zero, or Y strictly less than zero. Those three cases. And in a compact case of the Yamabe problem, people deal with the three cases separately, and usually the most difficult one is Y positive. Because it corresponds to include the sphere and include all those blow up, like the bubble situation.
So you have a group acting, non-compact group acting.
Yeah,
you have to divide.
Right. Yes. Okay, so
you have to deal with that, obviously.
In this case, our definition is actually a little bit different, because we are in compact support. So in some sense, Y positive include the Euclidean case, and include the spheres, because the sphere is a stereographical projection of the Euclidean. So it includes that part when you have Y positive here. Right. So what happens? So this theorem says that if you have Y positive, then you have convergence. So what happens when Y is less or equal to zero? So we also proved that when Y is less or equal than zero, then the flow must diverge. So it gives basically the criteria to distinguish between the convergence case and divergence case.
Does not converge. What does that mean? Do you know what it does?
Yeah, well, our paper also describes. So in the let me see.
I mean, does it oscillate? Does it move out to infinity? What is it?
Right. So it's given by this formula here. So in the divergence case, we proved that there are two cases. One is when the Yamabe constant is strictly less than zero. In this case, the conformal factor is O of t to the n-2O. So it blows up. It goes to infinity, it blows up. And it blows up, and we want to know what is this O. And in fact, we can describe it by using this equation. So in other words, the quotient of this by t to the n-2/4. So you quotient this to this side, it becomes a function. Yeah, rescaling it. And this one converges to a positive function that satisfies this special PDE. And this PDE, this limit is always positive, except that at infinity it tends to zero. But it's always at a finite point, it's always a positive number. So you basically have a very uniform control of what happens to this one. So this is a function that is everywhere positive and tends to zero times t to the n-2.
You have a good blow profile. Right?
We have a blow-up profile. And for the Y equal to 0 case, that was trickier. And so here I only wrote down the statement that it's the little o of t to the n minus 2 over 4, but it still goes to infinity because we have a lower bound. And that with the t lower bound, it is bigger or equal to that lower bound. So it still goes to infinity, but we do not have a very nice behavior of that quotient. We have some, well, at the end of the talk, I will talk about that. We have some sequential limit that goes to some equation that looks like this, but we do not have the global limit, like the global limit. We only have the sequential limit that goes to this.
We have different sequential limits, and you could have different sequential limits. Is that possible?
Yeah, in theory, it could happen because in that case, people know that the equation, the right-hand side in that case is 0, not -y anymore. And I think that this is some known knowledge about spectral of this operator that you have actually a family of solutions, all are positive and they are up to a multiplicative constant. So you have a phi that solves this equation and you have c times phi that also solves this equation. And for different sequences, it might go to different value of c. And it would be ideal to if one can prove there's a unique c that every single sequence goes to the same limit. Okay, so I think I'm up to here. So basically, we had 2 questions here, and we answered them. One is for the long time existence, it's yes, and also for the convergence, there are 2 cases. If the y is positive, then it's convergence, and if y is less or equal than 0, it diverges. And the reason that I marked these 2 red by the red text is because I want to point it out that up to here, the Ricci flow and Yamabi flow behave the same. So they both have short time existence and they both preserve asymptotic flatness and ATMS. But for the last 2 properties, they behave differently. One has long time existence, one doesn't have long time existence. And one has long time existence implies convergence, but this one always has long time existence. Sometimes it implies convergence, sometimes it doesn't have convergence.
Let me ask you, in the cases that maybe Brendel did, where he reproves, he recovers the existence of a constant curvature. He solves the Yamabi problem through the flow.
Yes. Yeah, whenever.
In the case when y is, say, 0, does he have it not converging or similarly?
No, in a compact case, you won't see that. In a compact case, okay, in a compact case, when y is less or equal than 0, it always converges.
Okay.
It always.
So this is new feature.
Yeah, in the positive case, it's much harder to prove, but so far, all the results that we have seen, the Strua, Brendel, and Rugang, previous Rugang Ye and Hamilton's ones are all convergence in the positive case. Yes. Okay, so I think basically we have done most parts, but we are wondering, like what Peter mentioned, and we are wondering what is the limiting profile. So let me just try to repeat a little bit, but in a more systematic way. So we're trying to understand what's the limiting profile, and this idea comes from the porous medium equation, because in a rough sense, it's a porous medium equation. If you look at the equation of the conformal factor. So this one, if you forget about what's the scalar curvature did here, this is like u to the power n, and you have a Laplace of u, and the usual porous medium equation is like you put this n to the other side. And however, the power is not. So this power n would be 1 over n there, and it's strictly less than 1. So the techniques of analysis is, in some sense, a little bit in the opposite direction of porous medium technique, but a lot of things are one can have a way to guess. Okay, so this is a result about the profile. On the one hand side, if Yamabi constant is strictly less than 0, we do this scaling, and we can show this converges to this function u tilde infinity, which is positive and satisfies this equation. Well, what does this equation tell me is that this is actually the scalar curvature equals -1 constant equation. So after doing the scaling, somehow you can still see the information of y negative, in the sense that the geometric interpretation of this, it's in the sense that when you do the conformal change by using u tilde infinity of this is the usual conformal power that we use, this extends to the unique -1 constant scalar curvature metric on the compactified space. So you have a manifold which is asymptotically flat. Of course, it's not a compact manifold. However, you can think of it as a stereographical projection near infinity, like what you do for the Euclidean space back to the sphere. And for asymptotic flat manifold in general, you can do that as well. And this M bar denotes the compactification of the flat manifold. So you just add 1 point. Yeah, you just add 1 point. You use certain stereographic projection. You cannot guarantee what's the metric behavior there at all. However, this thing that satisfies the previous equation tells me that after you compactify it, it has -1 scalar curvature.
So this convergence as t goes to infinity, in which topology does it happen? So is that the C infinity topology, or I mean this?
Oh, you mean this one?
Yeah, or the one before. Whenever you talk about something
Convergence.
converges,
Yes, that's a very good point. So we use this global weighted convergence, like CK alpha minus beta, the one that Bartnik defined.
You are working on this topology.
Yes, we're working on this topology. Because this is the topology that is compatible with this data. The data is in CK, then our elliptic theory considers about CK plus R2, and the data is in CK alpha minus beta with this one considers that in all the elliptic and parabolic Schauder as all those estimates. Yes. Okay, so the thing that I want to point out, and it's also going to be pointed out in my last slide about Oprah problem, is that we could prove in the critical case when y is equal to 0, it goes to little o of t to this power. However, we will also wanted to derive something that is similar to this case, that we want to describe the precise profile of that little o. However, we can only derive certain sequential limit behavior that I didn't present here, as it's a little bit too complicated to formulate. So there are some applications towards the direction of understanding ADMS along the flow. And as I mentioned earlier, it was known that under the flow of both Yamabi and Ricci flow, the ADMS is preserved constant. And after proving the convergence result, we could actually give the following so-called gap gap formula about the mass. So you have a metric to start the flow, and it has an ADI mass, and it eventually converges to something when the Yamabe, sorry, did I mention that? When the Yamabe is positive, then there is a gap between these two. And it's given by this formula that it's given by the limit of the integration of the scalar curvature along this flow. So the right-hand side is always a positive number. So before taking limit, this is always positive. So this is bigger or equal than 0. So you would have a m of g0 is bigger or equal than m of g infinity. So in other words, it gives a statement that, remember, this G infinity is the scalar flat metric. So in other words, it gives the proof that the ADI mass is minimized in the same conformal class by the scalar flat metric, because this minus that is always bigger or equal than 0. Okay, so I would like to point it out that there is another description about mg0 and mg infinity. This was used in Chen and Gilles' proof of the positive mass theorem. So they also give an expression of the difference of these two. And they didn't use flow, and their description is different. So they say m of g0 and m of g infinity, this is always bigger than that, and the difference is given by this quantity. Also, you can see r of g naught is positive, phi is the conformal factor, so it's positive. So the right-hand side is non-negative as well. So it's a different description, but ours is using flow, and theirs is like not using flow, but using the one that solves the, well, in some sense, this one uses just the elliptic equation, because phi is a conformal factor such that this one holds. So it solves the, phi is the conformal factor that solves the scalar flat metric equation. Okay, so let me just be very brief about what techniques we have used. Basically, we use three major things. One is that we use the L2 sublet inequality, and in the general asymptotic flat case and the asymptotic flat case with positive Yamabe, their behavior are different. So the first one is the general asymptotic flat case. We prove that there is sublet inequality. However, the constant depends on the time t. So if the flow starting from 0 to finite t, it depends on this t. And if t is infinity, of course, you don't have a uniform control of the sublet constant all the way to time infinity, but you have it for every finite time. And for the asymptotic flat metric with positive Yamabe constant, the benefit we have with this additional assumption is that we will have sublet inequality with uniform constant. And this constant does not depend on the time t. And that is really something that helps us to prove the long time existence. So both of these cases, prove the convergence. Both of these cases give the long time existence, but this uniform one would turn out to be a good decay of the scalar curvature and therefore the convergence. And another one that I would like to, the second ingredient about our, like the technical part is this Cantor-Brioux's result in 1981. So they proved the following two statements are equivalent. So they proved that the Yamabe positive is actually equivalent to say that the metric, the manifold admits a scalar flag metric on such a manifold. So these two statements are actually equivalent to each other in this asymptotic flag setting. All right, so this is the second one. And the third part is that we apply the Moser iteration. Actually, we've applied it 2 times. The first time we proved the scalar curvature tends to 0, and the second time we proved the scalar curvature has this good decay, decay of order -1 minus delta. So this is something strictly bigger than 1. That's a crucial thing. And this is basically the third part of this technical ingredient to prove the convergence. So after that, it's just using the global weighted elliptic and parabolic methods to prove the convergence. First, we have an unweighted version, and then we prove the weighted version. But the 3 main technical ingredients was presented earlier. Okay, so I guess I will just stop here as my time is up, and I will just leave this slides of open questions for you guys, and I welcome all kinds of questions. Thank you very much.
Are there any more questions?
So you mentioned the connection with porous medium, but you're not using any of the techniques there, are you?
Well, we kind of see the parallel pictures from the porous medium.
Yeah.
And we, for example, doing the scaling is the idea of porous medium. And you do the computation and you see that there should be certain spectral theory that comes in to help understanding the behavior of the blow-up profile. I think I'm not an expert in porous medium, but I'm trying to like borrow some intuition from there to understand what happens.
Porous medium equation has very special types of solutions, right? To maintain some compact support, but
yes, so I think over there, so here we have it defined on the whole Rn or non-compact set, but there they have this usually the bounded domain omega, and also the time here in my case is t goes to infinity, but there they have t goes to a certain finite number. So it seems that there is a relationship, but not like a very direct transformation of their problem to my problem.
So Ed Witten gave another proof of the positive mass conjecture using spinors and local analysis. Has that ever been used in any of this kind of Yamabi flow stuff? I mean, the critical thing that Chen introduced in the case that a Wang couldn't do was exactly the blow up at a point to buy compactness. And as you were explaining, it's in the variational thing, you buy compactness in the Sobolev inequality to get the critical point, which playing the role here in some way, I believe. But anyway, he's got a different proof, I think maybe for spin manifolds.
Yes.
Has that ever been used by any of this kind of analysis? That's all I'm asking.
I don't know, but I think that's a very good question. Yes. I feel maybe the problem with Yamabi flow is that it goes to the scalar flat one, but it not necessarily go to the positive mass like smallest one. But the Ricci flow seems to be the one that kills everything and eventually goes to the Euclidean one, but it seems to kill.
Well, the Ricci flow is making it much more proves the geometrization,
right,
so it's much stronger.
Much stronger.
But hasn't, for example, Lebrun used for example, Lebrun has used spinor methods.
Sorry?
Claude Lebrun to use.
Probably, I'm asking.
To, I mean, people using spectral methods, the spectrum of the Dirac operator to compute Yamabe invariance or to get an.
That's my question. Yeah.
Yeah. In the compact case, at least, or in special dimensions.
In other words, somehow the Dirac operator somehow You
Oh,
need
it
to go.
gives me a work of Hopkins and Brown, and they consider the Taylor case. They consider the Taylor case, and they prove some positive mass theorem in the Taylor case, but they need to assume some bisectional curvature positive condition.
Also, I think Bernd Ammann has been using spectral geometry for this type of questions. But I don't remember precisely.
All right, let's thank you again.